Hi, my name is Mariana, and I'll be presenting on gradient, directional derivatives, and path integrals. So to get started, what are they? So one thing that these three all have in common are that they answer key question of how a function changes locally, directionally, and over an entire path. So to break that down, first, a gradient measures or is a vector that measures the direction of the steepest part of the curve. And then a directional derivative measures how a function changes at a certain direction, which is a vector labeled v. So, for example, if a directional derivative is large and positive, then you're going uphill. But if it's negative, you're going downhill, down the curve. And if it's zero, you're moving along level ground. And so this means that the maximum value of the directional derivative is equal to the magnitude of the gradient vector. And while the directional derivative and gradients describe the direction of a certain point, path integrals continuously add all the changes the function experiences along a curve. So that means it adds together all the small changes that occur along the path from the starting point to the end point. So instead of just analyzing change at one point, the path integral captures the total change over a continuous period or motion. And so these concepts can be mathematically connected through relating and solving a problem related to hiking a hill. So every point in the elevation of the hill can be defined as a scalar function f of x1 and x2 equals 2x1 plus x2 squared. And so what if I wanted to know what the steepest direction of the hill is? So to find that, we can calculate the gradient. And the gradient can be found by finding the partial derivative with respect to x1 and x2. So then we can write it in vector form. So the partial derivative with respect to x1 equals 2, and the partial derivative with respect to x2 equals 2x2 because we use the power rule. And so therefore, writing that in vector form, the gradient, which can also be denoted as del f equals 2x2. And this is important because we can use it in the next part of our problem, where we want to determine how steep a hill is on a very specific direction. So to do this, we use directional derivative. And we'll define the direction vector v as 3, 4. And we will also continue using the same function that we used to find the gradient. So we already found what the gradient of f was, so now we need to multiply it by our direction vector, which again is 3, 4. So giving the dot product of the gradient and the direction vector, we multiply straight across, resulting in 6 plus 2x2 times 4, which got us 8x2. So this means that if I hike up this hill in direction 3, 4, then the steepness that I experience is 6 plus 8x2. Now, finally the third part, is a path integral. So let's say I wanted to find the total elevation experienced during my hike. So the accumulative change that I'll be finding in my path integral will be defined as the elevation gain. So again, using our same function, f of x1, x2 equals 2x1 plus x2 squared, let's suppose I hike from the path from point 0, 0 to 1, 1 in a straight line. We can then represent this path as p of t equals t, where t goes from 0 to 1. Now we want to parameterize our function to this path. So we'll define x1 equals to t because it corresponds to the x1 position here, and x2 equals t as well because it corresponds to the x2 position. Now we will replace our t's into our original function, which will get us f of p of t equals 2t plus t squared. Now the second part is to find p prime of t. Well, p prime of t equals 1, 1 because the derivative of t equals 1, and t is for both x1 and x2 positions. And then to find the norm of p prime of t, we have to square root 1 squared plus 1 squared, resulting in the square root of 2. So we have all our components of this formula, which is f prime of p of t times the norm of p prime of t dt. So we're just going to plug in our components. So we get 2t plus t squared times the square root of 2 dt going from 0 to 1. And so multiplying out the square root of 2 and using integral rules to get 2t squared over 2 plus t cubed over 3, we can now just plug in 1 and 0. And this results in the square root of 2 times 4 over 3. And so this number represents that the total accumulative elevation I experienced over the course of my hike on this hill is the square root of 2 times 4 over 3. So in order to summarize this entire problem, we can now say that our gradient is basically the compass because it looks at the direction of the steepest part of my hill, and the directional derivative is like my slope meter, and the path integral is my elevation tracker. So these are really useful values that we can use to calculate various things in the real world. So yeah, thank you. And I also would like to say that no AI was used and the work submitted is mine alone.